Hello everyone, I'm JD, and today I'm going to talk about the evolution of TiKV. And TiKV is a very complicated project, so you may not fully understand every improvement I'm going to talk about, but it's totally okay. As long as you get my point, we do a lot of things to make TiKV awesome and awesome. And let me introduce myself first. I'm a TiKV maintainer, and I'm also a 6 years Rust stations. And I run several projects like Raft Engine, gRPCI. And today's talk will involve 3 parts, and I will introduce TiKV first, and then I will talk about the evolution of TiKV as data set grows, and I will conclude the lessons we learned during the evolution. TiKV is a key value database. Compared to the existing key value database, it's distributed and it's transitional. TiKV has been adopted by industries, and here I just listed 4 of them. And of course, TiDB is the last adopter of TiKV. And TiKV was originally created by PingCAP to serve as the storage engine of TiDB. And TiDB is a distributed database. And on Tuesday of 2016, TiKV was first open source. And after about a year, it reached its 1.0 version. And in 2018, we donate the TiKV project to CSF and enter the sandbox. And it's graduated at 2020. We just released the 6.10 version today. And it's the first really long-term support version. Feel free to try. And here the graph, the OSS insights, will be after thanks to the community, after we join the CNCF, TiKV is getting more popular. Back days before creating TiKV, TiDB has tried to implement its transaction model on top of HBase, but it only found that it's difficult and inefficient to record shard transactions. So we have an idea, not just build a TV database that with building supports transactions matters. It's not afraid want transactions in their engine. So do it, and TiKV is created. And this TiKV was like a proxy on top of TiKV. And TiKV is serving as a building block, and the building block is very promising. Even some folks from our awesome community even build a Redis replacement on top of TiKV's transactional API. The project is named called Redis. Sorry, the project is called Titan Redis, and I'm going to show a demo about how it works. So there's a Docker Compose options. Let's check what it does. First, it will start a TiKV cluster, and then it will start the Titan Redis on port 7369. So let's bring the service up. Okay, it's up. And let's use the official Redis client to connect to the Titan Redis. And let's make a change. And it worked. And let's try its transactional APIs to see if it's really a transaction. So let's 9-6 key. We can see it's new, and let's walk through and start a transition, and we'll take. We can see change is queued. So then the 9-6 key is queued. So let's modify the key in another session. If it's really a transaction, then the key is changed while it's being locked, and the transaction will be read. So let's increment full. So full become 2, and commit the transaction. We can see an empty because all the checks within the transactions are discarded, and but it's still. So the transaction is complete. Based on TiKV's transaction APIs, the community can build a Redis replacement as high availability and scalability, and also durability. But how does TiKV itself improve scalability, availability, and durability? Let's check the architecture of TiKV. Key space is sharded into small ranges. We call those ranges as a region. It's not a good name. Let's deal with it. And every region will have multiple replicas. For example, region 1 will have a replica of node 1, node 2, and the replicas we are using aggregate to ensure consistency between replicas. And on top of TiKV is a placement driver cluster. Placement driver cluster is responsible to allocate the timestamp for transaction and also control where a replica should be placed. And the cluster speaks gRPC to the clients. So it's quite easy to develop on your own clients, your own service based on TiKV. Let's dive into the architecture of a single node. It's a layer design. On bottom, we use RocksDB as the storage engine. Actually, there are two RocksDB instances inside TiKV instance. The one is for Raft log, other for the data. On top of the RocksDB, we build multi-Raft implementations. And on top Raft, build a transaction layer using the two-phase commits and top two-phase commits layer. And on the top of transaction, we provide the QV API and coprocessor API. Coprocessor is the concept of coprocessor is borrowed from HBase. It will upset some special commands from client, execute the command, or listen for specific events. It's the mechanism of push down. So this is the initial implementation of TiKV. I just highlight some tests here, and first is sharding automatically. If the size of range exceeds, for example, 96 megabytes by default, and it will be split automatically. And in the early days, we use single thread to handle all the activities of Raft group. This for simplicity. And we use two-phase commit for transactions, and we have two ROS instance built. And the PD has a simple scale and times of record. You can see implementation, the early implementation of TiKV is fast. Because our philosophy is to make it work first, and then make it right, make it fast. And actually it worked. And it works quite well under the hundreds of gigabyte scales. But user data, the data of a user can scale. What if it scales to 10 megabytes? 10 terabytes, sorry. We have met our first challenge, the thread bottleneck. As I introduced, we use one thread to handle all the Raft activities within one TiKV instance. So the solution is quite just make it more ready. Every Raft peer is actually a state machine. So it's very intuitive to build an at-lab comparison system. And internally, we create batch system. So the batch system will fetch multiple peers in a batch, while in a batch, and then handle the activity, all the peers. Then the peer will generate all the readiness. Then the readiness will be written to disk at once. So in this way, we can both utilize the multi-threaded comparison and also achieve high write efficiency. And TiKV become popular. It's introduced to some latency sensitive scenario like callback. In those scenarios, every millisecond matters. There are two types of latency challenge we have faced. The first one is high transaction latency, and the second one is long running or short task. The second one is obvious, so I'm going to explain the first one. Remember that TiKV use two-phase commit to implement transactions. So when a transaction starts, for example, if you want to write multiple keys, a bunch of keys to multiple regions, then the client will divide all the keys into different regions and provide those keys to TiKV. After all the keys are written, we have a special key, or actually it's not special, but it's chosen arbitrarily. We choose an arbitrary key as primary key. Commit primary key. If the primary key is committed successfully, then we consider the transaction is a success. So it will return once to client. All secondary keys will be committed autonomously. The reason why we use two-phase commit is because we need to guarantee the atomicity across regions. For example, if we write to two different regions, and one region successfully write all the keys, and the other region fail. Without two-phase commit, there will be partial write, so the transaction is incomplete. But what if all the keys are located inside one region? In this case, we don't need two-phase commit, so we introduce one-phase commit. Because TiKV itself can guarantee the atomicity of a write. So it can just query a min commit timestamp from TD and send all the requests to TiKV. Then if it's pre-write successfully, then if it's written successfully, then we consider the session is finished. So compared to the two-phase commit, latency is reduced from 2 round trip to 1 round trip and plus one commit TS query time. Sorry. And I think the screen doesn't sync with my. Okay, now you work. And also, the count of keys written to TiKV is also reduced. Because in two-phase commits, we write all the keys once, and commit, we write all the keys another time. So that we write all the keys 2 times. But one-phase commit just write 1 time, so it's more efficiency. But the optimization is quite tricky because it requires all the keys located in the same region. What if they are still across the region and we also to optimize the our solution is a sync commit. The trick is calling all the secondary keys decide primary keys. So whether the transaction succeed or fail is checked by whether primary key is pre-written successfully and the secondary keys in reference are also written successfully. So after pre-write, we can consider the transaction success. So we can return success to client and then commit both primary key and secondary key in a sequence way. The latency is reduced just by one phase commit, but the keys needed to be to write TiKV is the same as two-phase commit because it's still two-phase commit. Is that clear? Okay. And for the second problem, long-running will block short-time tasks. We build multi-level feedback queue. The queue will have multiple levels. At first, all the job will push to the level 0. If it's too much time, then we will pause and be in queue to the level 1. If it still takes much time, finish, it will be paused to the level 2. Level 0 will have higher probability to be logged out and executed compared to the level 1. It's the same for level 1 compared to level 2. So all jobs we can finish in, for example, within 5 milliseconds, and we always get to be executed. The downside is that the long running will take more time to finish, but the good thing is that short tasks will not be blocked by long running tasks anymore. And we actually made this as a standard along queue. If you want it, you can just try it. And as TiKV gets changes never stop, and users' data keeps the problem at tens of terabyte scales. But what if the data scales to hundreds of terabytes? It's not an assumption. It's a serious. This is a screenshot from one of our clients. Their data set that the storage reach more than 500 terabytes, but it's free replicas. So the total data is about slightly less than 200 terabytes, and the region become more than 1 million. So the challenge is quite obviously that when data scale to more than 100 terabytes, we will face the problem that we may have too many regions. As we talked before, TiKV use Raft algorithm to ensure consistency in replicas. So if we need resource like CPU memory to drop the Raft activity, if there are too many regions, then there will be a resource waste. If we higher CPU all the time. And also, if there are too many regions, then there will be too many metas. And all the meta will be stored on PD. So it will cause high pressure on PD. On the other hand, RocksDB doesn't work well at large data set. The reason is RocksDB is designed for general query, but our usage, for example, we have two RocksDB instances. One is for storing log, is for storing data. And RocksDB is not designed for storing log. So to solve problems, we first introduce hibernate regions. In normal systems, not all the data is hot. Actually, usually there will be 80% of data are cold. All those Raft groups will never serve any read-write requests. So in this case, we will put those Raft groups to sleep. So there will be no habits, no Raft activity. So the CPU usage will be reduced. And also, the cluster will always be empty. When there are new versions or data get deleted, the size of a region becomes small. In this case, we introduced the merge algorithm to merge a small range into a bigger range so that it best fits into the size configurations. And for the data storage engine, we introduced Titan. Titan is inspired by Whiskey. And the basic idea is to separate the value from key value, separate the big value from the key, store the value into the block file. So LCM we only have we only have keys and small. So during the comparisons, data set involved will be way smaller than before. If there is no keys in LCM reference to the block file will be deleted. So the comparison cost will be very small. There's a difference between Whiskey and Titan. Whiskey will write all the values to the value log, but Titan will write key values to while ahead log. The reason is that we want to keep best compatible with RocksDB. Actually, Titan is developed as a plugin of the RocksDB. So there is no compatible problem. And in our benchmark, it brings 3 times write through improvement when value is KB. And it's also a standalone project. If you are interested, you can also have a try. And for the log storage, as I explained, RocksDB is not designed for storing log. So we instead of a lot of turning, we develop our own region, our own Raft Engine. The idea of Raft Engine is log are always append rate, and it will get truncated very frequently. So we will write all the log into a series of speeds, and then all the logs within a file is truncated, the file will be just deleted. So less compression compared to RocksDB. Our test also the effective results. We reduce the tail latency 20%, and also the bytes written to disk is reduced by 40%. As we solve, as we make TiKVs proceed to scale to hundreds of terabytes, we solve major problems of scaling. So there will be more and more requests from the business. That is higher whole one data separation and compliance. All are complicated requirements, but we found there is some comments in those requirements. That is, user want to customize how the data is placed. So we develop efficient placement rules. In the past, PD used global static placement rules to apply to all the ranges, and now the rule work on ranges. For example, if meta range is quite important, you want to increase its durability, then you can just write rules to increase the count of replication. And for some not important range, and you may just reduce the replica counts to reduce cost. So the solution may not solve all problems, but it solves the most of the requirements. And also, as TiKV grows, we found many users tend to use TiKV on the cloud. And the cloud environment is quite different from the on-premise. As a KV database, the first thing we want to know is where should we store our data. Take database as an example, you can load disk, EBS, or S3. As if you want to local disk is not reliable. It doesn't recover from the start. And S3, the latency of S3 is quite high. So it doesn't work in latency sensitive situation. So EBS is a balanced choice. And for EBS, the LPS and bandwidth are money. The less you require and less you pay. Also, EBS has a burst feature that will allow you to use more LPS or bandwidth you have required. But why we say it's a poison apple? Because in our benchmark, if we run out of the burst quota, the performance will become very poor. In TiKV, in the original implementation of TiKV, the CPU bound job and IO bound job mixed together, because TiKV is designed for the local disk in the past. So it expects the IO job will finish very fast. So it doesn't block the CPU bound job. So the IPS required is pretty high. But it's not the situations for EBS. So it developed a new feature named asynchronous rough IO. The idea is just separate CPU bound job and IO task. So IO bound task will be batched up and finish in another batch with a limited rate. It may seem quite simple, but it needs to change the core rough. I should say it need to check the core rough implementations. So reasoning the change, whether the change is correct, is hard, and we make a lot of tests, but we found that only one key line change needs to be made. And the change is all landed in our open source rough library. You can have a try. And our experiment shows that there are about 10% improvements in throughput and way less jitters. Also, we introduced rate limiter. Rate limiter will hook all the background jobs like compression, flash, and foreground jobs. So it will ensure all the jobs will not write more data configure value to the disk. So it will not trigger the burst quota a lot, but it's a soft limit. So just in case if you still use the burst quota. And we have solved the problem that data scale to hundreds terabytes. But what if the data scale to 1 petabyte? Remember the screenshot we showed? To serve hundreds terabytes, our customer use more than 200 TiKV instances. If the data scale to 1 petabyte, there will be more machine required. For example, if this cluster have 1,000 machines, it's quite normal that some machine will just crash, broken for any reasons. In this case, the scaling speed is critical. If a machine is down, you need to quickly move all the data down machine to the new one. In the current architecture of TiKV, if the data of one node, if a node has several terabytes to scale in the node, it will take hours, perhaps probably in 24 hours. And to scale out the node, it usually take days. So it's pretty slow. And on the other hand, if you want to raise the capacity of a single node to reduce the total counts, then you will face the RocksDB performance issues like compressions and its global locks and all the other things. So to solve the problems, I wrote a proposal. It's not implemented yet. In the current architecture, all the regions will share the same RocksDB instance. So the data inside the RocksDB instance is logically split. And in my new proposal, every region will have its own RocksDB. So scaling a node is simply just copy all the RocksDB from one node to another node. So the speed will be very fast. Our prototype has shown that it can bring 4 times speed improvement in scaling and 3 times in scale out. And during the whole process, the throughput is very predictable and smooth. But as I said, it's still a proposal. If you have any thoughts on my proposals, you can just go to the RFCs and leave your comments. Sure.
So in this slide, each region is a period, is a chart, right? So in this case, going to increase the resource per node. Since now you are running like RocksDB.
Yes. You mean
like memory? Like now, previously, I guess you have only one RocksDB for all of these to share the same thing, right?
Yes.
Now you have a lot of RocksDB instances, which means they are competing with themselves.
Yes.
Right? It's called like noisy neighbors to each other. How if you don't increase the resource, like how do you mitigate that?
First, although we have multiple RocksDB for inside a region, inside an instance, but we still share the same rough log. So the actual data written to the disk is amplified by the multi-RocksDB architect. So the disk resource, we don't need to worry. And yes, but SQL is in background. So we actually RocksDB supports to share the environment is shut in RocksDB, define the file system size and things. So we made all the RocksDB instances share the same environment, so we can control the rate limits. Okay, and although the file system is not an issue, but the memory is truly an issue. Our goal, say we can do that now, but our goal is to make it make a 8-core 32 gigabytes machines can host 1,000 more than 10,000 RocksDB instances, and there is still a lot of work to do. And for the CPU, because the RocksDB are isolated, so actually there will be way less comparisons than before, because when they are share the same RocksDB, if you move a shard out, you will need to change the shape of the RocksDB, so it will bring a lot of comparisons. But in the next, there will be no issue. So it will be way less comparisons than before. So the CPU, we didn't see it becomes an issue yet. Okay. Yeah.
So during the scaling, any affection for the breakpoint?
It's actually, it depends on the rate. It's not the because of course it will always affect the online, and no matter the old way or the new way. But in the old way, if you bring a lot of connections, that's the actual effect that affects online query. But in the new way, there will be no connections. So the only factor that affects online queries is the rate that writing all the data to the disk. It depends how fast you want. If you code in an acceptable rate, the effect to the online query is quite small.
Okay, but yeah, I think the RocksDB compression could like in the CPU work.
Yes.
Yeah, that would affect the performance.
Yes, but the new architecture is no difference, because we physically copy the physical RocksDB from one node to another node.
But you use like this is like a peer-to-peer copy.
Yes. Okay. So it has there we need to ingest the SD file to the new RocksDB, right? To the new node. Okay. But in the new way, there's no ingestion. You just simple. Oh, it copied the RocksDB to the new node. Yes, and TiKV take over the directory, just a pure rename. Yes. So other questions? Okay. So EC and N, we need to consider that whether the data will scale to tens of bytes. I guess no, because I haven't seen any cluster that reach the limits yet. But there is other questions that we have think about, but we don't have a correct, bad answers now. For example, what is cloud native? TiKV has called itself as a cloud native distributed keyword database past. But as the evolution of technology and change of environment, at least myself, think that may not be a statement. What cloud native actually is using Kubernetes cloud native, or is deploying in it, or is using S3 is cloud native? I don't have a clear answer now, but I think be cloud native, be very native. For example, we can use all the resources that cloud can be applied, or the most cloud providers can apply, and instead of using some deployment. And also, remember we use PD to allocate time for transactions. If the cluster is deployment clause regions or clause available zones, then timestamp allocation will become very slow because it needs to go through the round trip to another available zones to acquire the timestamp. Spanner doesn't have such problem because it uses true time. And in the recent years, AWS also introduced true time to their architecture. So will the true time be the must to have in the future cloud service providers? If that's true, is it more beneficial to true time instead of timestamp oracle? I don't have an answer for now. And the hard question, what will it look like if we design TiKV from scratch? Evolution is a long journey, and we learn a lot of things during the journey. And the first thing is build a distributed system. Back to days, we created TiKV. We think this is quite simple. Just do it, and we did. But actually, we are wrong because it's quite hard. You will meet a lot of challenges. But if you have to do that, then just do it. It's a hard journey, but have a lot of fun. And second lesson is choose the right architecture. As you can see, except the 1 petabyte parts, before 1 petabyte, the architecture of TiKV is actually the same. The evolution always happens in the small parts. I think choose the right architecture is the key reason why we can evolve so rapidly. And keep rolling. Obviously, as technology with all the new technologies, there's no silver bullet to solve all the problems. You have to change the products to meet the user requirements. And with community, we didn't TiKV from scratch completely. For example, we use RocksDB as our storage engine, and we port the Raft implementations from TiDB. And we also contribute a lot back to the community. Besides all the awesome projects I list the list, we also have other projects in the TiKV. And that's all. And this is the URL. This is the repo, our repo. Any contributions, welcome. Thank you.